Welcome to The Explainer. Today, we're diving into something literally colossal. We are stepping right into the fascinating and honestly mind-blowing world of modern maritime engineering. We're going to explore how humanity constructs some of the absolute largest, most complex moving structures on the entire planet. We're talking massive vessels, thousands and thousands of tons of steel, and the incredibly highly orchestrated process that actually brings them to life. Specifically, we'll be breaking down the whole block construction method, or HBCM, a methodology that completely revolutionized the global shipbuilding industry.
But first, picture this. Imagine the sheer logistical nightmare of the past. For decades, ships were built from the keel up in a dry dock, plate by plate, piece by piece, in this strictly sequential order. This meant cramped working conditions, a huge reliance on good weather, and most painfully, it completely bottlenecked the entire shipyard. The dry dock was just occupied for massive lengths of time, totally crippling production speed. So the multi-million-dollar question became, how do you build a colossal 90-meter vessel without paralyzing your shipyard's most valuable real estate? Well, the answer actually lies in breaking the ship down to speed the process up.
So here is our blueprint for today. First, the HBCM revolution. Second, block division and stability logic. Third, the 85% pre-outfitting advantage. Fourth, managing modern shipyard workflows. And finally, the future of maritime efficiency. Let's get right into it.
Section 1. The HBCM revolution.
Okay, let's dive into this. The shift from traditional sequential construction to the whole block construction method is honestly a lot like moving from carving a sculpture out of a single giant block of stone to assembling a highly complex Lego set where multiple people are building different sections at the exact same time. HBCM allows shipyards to divide a ship into three-dimensional blocks, and because these blocks are fabricated in parallel, off to the side in controlled workshop environments, you completely eliminate the weather delays and those cramped conditions of the dry dock. This is exactly how HBCM optimizes shipyard production, by allowing multiple streams of work to happen simultaneously, drastically compressing the overall project schedule.
Now, you don't just magically start with a massive block, right? You start with individual parts. We're talking steel plates and profiles cut with high-definition plasma or lasers. These parts are then welded into flat or curved panels. Then, those panels are joined to form a three-dimensional block, typically weighing anywhere from 50 all the way up to 400 tons. But wait, it doesn't stop there. Shipyards will often join multiple blocks together right on the ground to form what's called a grand block or a highly outfitted module. Before ever doing a final lift into the dry dock, it is just a brilliant hierarchy of assembly.
Section 2. Block division logic and stability strategy. And this brilliantly illustrates the whole concept. For a typical 90-meter offshore patrol vessel, engineers will slice the design into roughly 55 to 75 distinct blocks. The engine room, which is super complex, might be split into 6 to 8 blocks, while the bow might be 4 to 6 blocks. Side shell blocks are usually made symmetric, port and starboard, just to simplify production. But this spatial division isn't just about size. It's a highly calculated strategy to optimize stability, welding access, and overall shipyard throughput.
Now, the block division logic behind stability and construction relies on some really strict criteria. First and foremost is structural integrity. High-stress butt joints must be carefully managed and placed across block boundaries so the ship's overall strength isn't compromised at all. But you also have sheer physical limits. Mid-size yards typically have crane capacities of 300 to 600 tons. So a block literally cannot exceed what the yard can physically lift or transport via its internal roads. Finally, the division must support a logical erection sequence. If the blocks can't be pieced back together in a stable, structurally sound way in the dock, well, the whole plan falls apart.
Section 3. The 85% pre-outfitting advantage.
I want you to imagine building your house, completely sealing up all the walls and the roof, and only then trying to squeeze inside to install all the electrical wiring and plumbing in the dark. Sounds crazy, right? Well, that is how traditional shipbuilding worked. Today, HBCM changes that. Because blocks are built open and in workshops, workers can install pipes, cables, HVAC, and heavy machinery long before the blocks are actually sealed together. Leading shipyards target a staggering 70 to 85% pre-outfitting level for complex spaces like engine rooms. This 85% pre-outfitting improves production speed monumentally, mostly because workers are operating in comfortable, well-lit, open-air conditions.
So the crucial point is really understanding how deep this pre-outfitting goes. The industry defines 4 distinct levels. Level 1 is just your bare steel structure. Level 2 adds basic pipe runs and cable trays. Level 3 is advanced. We're talking complete piping with valves, electrical distribution, and heavy equipment installation. And Level 4? That means the systems are actually pressure tested and ready to turn on. By hitting Level 3 targets for engine blocks, shipyards dramatically slash the amount of time the vessel has to sit in the dry dock. Basically, how pre-outfitting reduces dock time is directly proportional to how much work you pull forward into that workshop phase.
Moving on to Section 4, Managing Modern Shipyard Workflows. Now, what's really interesting about this slide is the human element. When it actually comes time to erect the ship, meaning lifting these massive blocks into the dry dock and connecting them, it is a hyper-precision operation. Notice the workers utilizing highly calibrated laser trackers. They use these, alongside total stations and photogrammetry, to establish a flawless 3D coordinate network for the entire dock. They are continuously verifying the alignment as those blocks are slowly lowered.
And the margins they're working with here are, frankly, staggering. We're talking about lifting a 400-ton grand block, swaying from a massive gantry crane, and landing it with a required misalignment tolerance of just 1 to 2 millimeters, and a gap perfection of 3 to 5 millimeters. The contrast between the immense crushing weight of the steel and the microscopic margin of error is just incredible. If the alignment is off, the structural fairness of the hull is completely compromised. It requires hydraulic jacks, temporary supports, and absolute mastery of thermal distortion during welding to get it perfectly right.
Finally, Section 5, the future of maritime efficiency. To keep this massive 4D puzzle from falling apart, modern yards rely on advanced software like Synchro, Navisworks, and specialized ERP platforms. A detailed 3D model of the vessel is tied directly to the project schedule, creating a 4D environment where planners can literally visualize the block erection sequence over time. They can identify spatial conflicts before a single piece of steel is ever cut. In fact, yards that have fully integrated these digital twins and structured work breakdowns report dock time reductions of 20 to 35%. They are literally building the ship digitally to ensure the physical build is totally flawless.
Which leaves us with a really fascinating thought to end on. We've seen how the hull block construction method completely reshaped the physical constraints of shipyards. We've seen how pushing pre-outfitting to 85% slashes dry dock time, and how millimeter precision manages these incredibly massive structures. But as we look ahead, in an era increasingly driven by digital twins, AI analytics, and 4D scheduling, is software now just as critical as steel in building the ships of tomorrow? It's an incredible evolution, going from sequential steel cutting to full-blown digital orchestration. Thank you so much for joining me on this explainer, and keep questioning how the world around us is built.